All right, let's get started. So I guess the few that I haven't managed to scare off are, well, half of the whatever's left are scared off by the temperature in the classroom, probably. So today, I suppose we're switching on from linking, and we're moving on to the process abstraction and process control, that sort of thing. First, any questions on the homework?
What exactly do you want done on part 3?
Well, I want the program to run correctly, show the animation and all this, but not contact the server.
So you don't necessarily have to mask RIP. You can just.
There's no masking. I mean, it's not actually possible to mask the IP. You gotta just not talk to that server.
So we don't get both powers.
What's that?
There's no way to it's not grabbing your IP in a way that we can send it a fake one.
You have no way to fake it, no. And that's true in general for a TCP connection. You can't fake it unless you have someone who's collaborating with you that you can put the blame on, but it's not really faking it that way.
So basically, our goal is to actually connect to the server at least once, grab the function, and then hard code it.
Exactly.
And
Yeah.
then skip over the connection.
Right. So you have to do it once so you can see what the server is actually doing. Maybe you can make a guess, but it'd be easier to just see what the server is doing. And maybe a good idea would be to put a breakpoint after it's fetched the code, and then just with GDB see what's in there, see wherever it wrote it, and see what it put there. Another way would be to talk directly to the server. You can use netcat, but you haven't taken CS450, so those tools may not be in your repertoire yet. So maybe the easiest is just to see whatever the program's doing, stop it before it exits, and see what's in there after it's fetched the stuff from the server. That's one way. Yeah.
So with GDB, you can't actually see what assembly line you're on in real time. I think I posted a question on that, and you said just to look at the PC counter.
Right. So the program counter says which line you're on, so that should help.
Wouldn't it be? It's based on the C file, I thought, not the assembly line.
No, a program counter isn't based on that. So you see something, it just says, on a break it says, oh, this C file, this line number, but that's not actually the program counter. So if you, I don't know how you get the program counter directly, but if you just say info registers, that'll be one of them. Right? It'll be RIP on a 64-bit machine. And then you can use GDB to print out a range around there. Maybe if you use object dump, you may not get the. I think you can, with some flags, you can tell it that you want the virtual addresses rather than the addresses inside rather than the bytes offsets inside the file. So that would be. I mean, it can be a little tricky to figure out which byte in the file corresponds to the program counters. I think they're flags to object dump, but I'm not 100%. Other questions on homework? Oh, yeah.
I just see this kind of general, but how long are you anticipating that this should take us on?
It is very hard to guess. It is a very easy homework if you if the concepts are obvious, then it's a very easy homework. It's probably the easiest one yet. But there's some things that are not so obvious. So
Is it like last time was more execution, or is it more understanding what's going on? More understanding what's going on?
yeah, the execution is so minimal that I mean it's literally just writing a few bytes into the program. So the execution you can't do that much. But so one thing that's really hard, for example, is I'm gonna do a jump now. Like I wanna jump somewhere where it didn't used to jump, right? Or I changed the code a little bit, so I need a new relative jump. That can be a real bitch because first of all you got to have these negative hexadecimal numbers, and it's easy to get that off by 1 or something, right? So you say, oh, I want to jump like 50 addresses up. What does that mean? Okay, so I have my jump that's probably E8 if I remember right, and then you got to put a 4-byte address in there or an offset, and it's not an absolute address; it's an offset saying -50. So how do you figure that one out? Okay, that's a little tricky. It's very easy to get it off by 1 or so. What I suggest is you type something in, then you run object dump on your new binary, like you make the new binary out of the hex code again, run object dump on it and see, does it actually jump to where I wanted it to jump? All right? Because if you just run it, it's going to crash. It's always just going to crash on you until you get it exactly right. So you run object dump, and you see, oh, is it jumping to exactly the line I wanted? Okay, then you're good. One very tricky thing that I mentioned to some people after class is the jumps. Well, okay, so the object dump output, it has some address. For every instruction, it's got an address. That points at the beginning of the instruction. The instruction, of course, has a length of some bytes. If you do a jump, the jump happens from the end of that instruction. These jumps are 5 bytes long, so usually, if you just do the math based on the addresses on the left, you'll be off by 5 bytes. It might be 5 bytes too many, 5 bytes too few, depending on which direction you're jumping.
Oh, that explains that.
Yeah, okay, good. So, yeah, so just watch out for that. So again, if you do it with object dump, it'll just say where it's jumping to, and you say, okay, how did I get this off by 5 bytes? Okay, let me add 5 bytes then, fine, and it's done. All right, so you don't actually have to necessarily do it right from the beginning, but yeah, that's the trick. The jumps are from the end of the instruction. Okay, up.
If you run this locally on a 32-bit machine, if you're not around a Wi-Fi connection over the weekend, the binary is going to work. You run over to 64-bit.
It's not. The binary isn't going to even run on a 32-bit machine, I think. If you get it to run, I'd be happily surprised. But the thing is, the address space layout is going to be different in different machines, and that's also why we're turning off this ALSR, the address space layout randomization, ASLR, because it even differs in one machine if you don't turn that off.
But so like if I'm put on a 32-bit, 64-bit, then like the fun testing on that.
64-bit Ubuntu machine should be fine, yeah. But again, your safest bet is to do it on EC2. Okay, so let's get going with processes then. So I think we talked a little bit about processes before, but let's recap a little bit. So okay, processes. So this is an instance of a program, right? So you can have a single program can be running multiple times on the same machine. It's different processes. They've got nothing in common. Right? Those two programs, they don't communicate. They don't share variables. They don't do anything except that they happen to have the same code in memory. There are a few things that are unique to each process that are part of the process abstraction. One that we've dealt with a lot so far is their own local address space. Call it process local address space. So even though lots of processes are sharing the same memory, it looks to each process as if they have their own memory. Right? Each process, they cannot see whatever's in some other process's memory. There's no way for them to even address that memory under typical circumstances. So there's complete separation between processes when it comes to memory. So that's nice because that means the machine we can just run some instructions and we don't have to worry about what they're going to do. It's not going to destroy anything for any other process. We don't need to coordinate with other processes at all since we have this separation. We can just run our stuff and then sometimes we get an exception. We'll talk more about exceptions later. If we try to do something that doesn't really fit within the current setup of the process. But what are some other things then of a process? Well, it has its own flow of control. So this seems fairly obvious. So anytime we program, we write the program and it's just like one long series of instructions. And we somehow assume that they will all be run in sequence except when we're jumping and then we're jumping to where we were saying. And that's about all there is to it. But on at least a few years back, everyone just had a single core. You just have one CPU, has one set of registers. Let's not talk about hyper-threading right now. So there's one set of registers. And yet we can run multiple programs. So how does this work? All right, somehow the computer, well, the hardware and the operating system are cooperating to make this illusion that there is a constant flow of, or a uninterrupted flow of control for each process, and they're running concurrently. Yeah, it also seems to the processes as if they're all running at the same time, but of course they're not. There's only one CPU, there's only one set of registers again, so they cannot run at the same time. They have to share this resource. Okay, so mainly here, okay, so maybe we call this sharing a single memory resource. Single memory, that's fine. Here we're sharing a single CPU. And in both cases, the process can't even tell. We want there to be an illusion of this being the sole property of each process. Okay, what are some other things that is specific to a process here? Well, I guess there's our file descriptors. So those are a really strange phenomenon. They're actually a number. We've seen this so far. There's just an int, right? A file descriptor that int can be backed by all sorts of stuff. It can be a network connection to the rest of the world. It can be, or that is to one other server somewhere else. It can be an actual file. It can be standard in, standard out. It can be a serial port, and the raw disk if you want. It can be all sorts of stuff. So every process has this range of integers, and each file descriptor is then inside the OS, each integer backed by a struct that says something like, oh, what is this? And how far have we gone so far? Or where are we reading at the moment? Is our, what's it called? Cursor, maybe. Okay, so there's actually a couple of different kinds of files. There are those that you can seek and you can go back and forth. And then there are those like a serial port, that you just get whatever is coming in. And it's not like you can back up and see what they said earlier or move forward. Okay, so those are the main aspects of a process, and they're all individual to every process. So everyone has a standard in, right, but it's a different standard in for every process, and we try to manage that in the back to make it sort of work intuitively for the user. All right, so let's look maybe at one of these. Let me see so I'm not missing anything important here. Yeah, okay. So perhaps one more thing. It has it runs in user mode. Okay, so who's heard of user mode and supervisor mode before? Kernel user mode. Okay, so only a few people. So what does this all mean? User mode basically means you're not allowed to do almost anything. Right? There's only a couple of things you can do as a user. You can read and write from memory, run normal instructions. These are non-privileged. And the normal instructions are things like, oh, jump, add, things like this. Right? It's not change the page table entries. Right? It's not all these special registers in your CPU that changes how the CPU actually works. You can't touch that. There's very little you can do there. Oh, and from memory, this is only those pages indicated in the page table. Okay, so the page table, if you recall, is what controls this shared memory, the process local address space. So if there's no entry in the page table, you're certainly not allowed to read or write from that part of your address space. And if the entry says this is a read-only, then you're not allowed to write, and so on. And there's also a little bit that says you can only execute this if you're in supervisor mode versus if you're in user mode. So you can't even jump to it if it's supervisor mode. Okay, so how can we do anything useful with this sort of program? Or with this sort of situation? And it's pretty limited here. For example, printf. That doesn't work. We wouldn't be able to print anything. Because what can we do here? How would you communicate with the user? You can read and write from memory to from memory, from to. But we want to put something on the screen. And so the screen isn't in memory, so therefore we can't do it. What if we want to send something to the rest of the world? We want to do a network connection and send something. We can't do that because that's not in here. All we can do is read and write from memory and then run some regular instructions. It's not like there's a established socket connection instruction in your CPU. So that doesn't work. We can't even write to a serial port because a serial port isn't in memory.
Can you also share a shared library to do it for you?
Shared libraries are, as we know, they just get linked into your program. So they also have exactly the same restrictions. So this is a bit of a problem. The process actually can't do anything. We can compute whatever we want, right? But we can't probably read any input, and we probably can't output it. So it gets a little bit limited for a program. So we need one more facility, and that is you can cause a software interrupt. Okay, so that's on the 32-bit machines. That's called int. You probably maybe have seen this if you looked at any assembly code in practice. On a 32-bit machine, int 80 is very popular. On a 64-bit machine, there's something extremely similar but doesn't have the same name. It's called make a system call, and the opcode is syscall. Okay, so they're basically the same thing. Okay, so what's a software interrupt? What's that? A priority? No, it's not a priority. At least not the way I understand it. So let's forget the software interrupt. Just an interrupt in general. What happens when an interrupt happens? Like what does the CPU do? It stops. And then that's it. Oh, that's a problem. Because now, okay, so we can compute some stuff and then we can stop. It doesn't make the program much better. So it does something more with an interrupt.
It gives access for another program to run in that place.
Did you not talk about interrupts in 261?
No.
Oh, okay. I suppose it will be covered in 362 then. But
Processor interrupt 362.
right, exactly. So this is the same thing. Processor interrupts.
Sending a message to the processor that the processor will.
Yeah, or usually in a hurry. It'll read it right away if it can.
To polling, I think it is.
Yeah. Okay, so I should make a brief introduction to interrupts then. What is an interrupt? So the typical interrupt that you see in hardware is there's a little pin that goes into the CPU. Right? The CPU has a few hundred pins on the bottom. There's a bunch of those pins that if you touch it with some electricity, the CPU stops. Right? It goes and does something else. So by touching with some electricity, you could be another chip. You can connect the pin to high or maybe to ground, depending on the setup. And then that causes the CPU to stop whatever it's doing and immediately start running some other instructions. Okay. So it stops current flow operation, flow of control, immediately runs some other code. Okay, so what is this some other code? It's indicated in what's called an interrupt vector. As a bunch of pointers. So it maps interrupt number to address. Okay, so this is, well, it's an array. I call it vector, but it's an array. So say now an interrupt happens. The 5th interrupt pin on the CPU is triggered. The CPU immediately stops, looks in the 5th entry in this interrupt vector and says, oh, okay, let me go run that. Okay, so it always jumps to a known address and runs that code. And then you can return from this interrupt. It's IRET is the instruction. And then you just go back to whatever you were doing. So you're running your nice program. Someone hits a key on the keyboard. And it doesn't, these days it usually doesn't trigger an interrupt, but in the past it would trigger an interrupt. The CPU would stop, figure out what happened on the keyboard, get that, your little program that you probably put in there now, reads from the pins on the keyboard to figure out, oh, what is being touched, right? Puts the letter in a buffer somewhere, returns. It's now your program continues computing, you keep typing, everything's sort of working at the, it seems like you can both type at the keyboard and your program is running at the same time. But it's not really the case. For a brief moment, the program stops, it reads from the keyboard, and then you come back. So how is any of this going to help us with printf?
And how does it affect the stuff that's in the registers?
Can you say that again?
How does that affect the things that are in the registers as well?
Oh, that's a very good question. So when an interrupt happens, you can do whatever you want, in which case you will screw up the execution of the program, and it's no good. So whenever an interrupt happens, usually the very first thing you do as an interrupt handler, that little program that gets called when the interrupt happens, is save all the contents of the register. Put it somewhere else. Usually you then change your stack pointer to deal with an interrupt stack instead of the usual program execution stack. And then you do whatever you need to do, and you return, and before the return, you restore all the values to the instructions, to all the registers, put back the stack pointer, and then you return. Okay? So what's really nice about interrupts is that they are run in what's called supervisor mode. If you're, okay, I should put that. Interrupt handlers run in supervisor mode. Okay, so any guesses? What does the supervisor kernel mode let you do that you can't do in the user mode? Whatever you want, exactly. Okay, you can do whatever you don't want. You can poke directly at hardware at memory addresses without this virtual memory stuff. You can turn off the virtual memory if you want. You can look at the contents of any process, do whatever you want. Screw up all the hardware. You have unlimited control. And of course, one of the most important things you can do that you tend to do often if you're hacking this sort of stuff, crash the machine. Right? And we do a lot of that in 385. Okay, so this is handy because when you're in supervisor mode, now you can do whatever you want. And if your program can cause a software interrupt, then we can actually get into supervisor mode. Right? So we can be in user mode and then somehow transfer into supervisor mode and get those whatever you want done.
But in that case, why ever run an
Because you can't run whatever instructions you want. So when you cause a software interrupt, you jump to a specific address. Right? So that doesn't seem very useful. I want to run my program, not whatever someone else put in there. And that someone else, of course, is whoever wrote the operating system. All right, so what we need to do here is have some facility in the OS that allows us to say what we want the OS to do. All right, so we cause an interrupt. The only interrupt that we typically would cause as a user space program on the 32-bit machine is this int 80. It's a single interrupt. Okay, that doesn't seem very handy for printf. Unless you want to have printf there, but then what are you going to do when you want to scanf something? So, any ideas?
table?
A table. What are we going to do with a table?
I have no idea, but everything seems to be based on tables these days.
Ah, I see. Some level of indirection. Yeah, that's usually what happens. So, before we cause this interrupt, we need to somehow tell the OS what we meant by this interrupt. Right? And this int 80 is not enough. That just jumps to some address. So at that address, the OS can have whatever instructions they want, but it'll always be the same instructions. So we can have some instructions that say, instead of just saving away the registers, they see what's in the registers and interpret that to see what you meant. Right? So, for example, we can put a number in EAX, RAX, saying what did we want to do? Okay, so in Linux,
Is this way said there's only about 200 system calls for a while earlier this winter?
yeah. Let's just see. Oh, here it is. Okay, these are the things that we can tell the OS to do. There may be a few more, maybe some were added lately, but that's about it. Okay, so those are all the functions that we can call in a sense. So we never actually get to call there. We can't say call and then the address of that function. We don't even know where that function is. But what we can say is put here, and it even says, that's very nice of them, in EAX, we put the value syswrite. Okay, 4. We put a 4 in EAX. That means now that, I caused this interrupt because I want you to write something to somewhere. That's not enough, but now, just like with the regular functions, we can stick more values in other registers if we want. We can put them on the stack, so on. And now the operating system can see, and you wanted to write to this file descriptor, and you wanted me to write this string for this many bytes, just like you would with a regular system call, except they're kind of, the values may not be in quite the same place. Okay, so now we have facilities to do all sorts of other stuff that we're not usually allowed to do. The reason why this is safe, of course, is that the operating system has the implementation of all this. We trust the operating system to protect us from doing bad stuff and protect us from other processes doing bad stuff. So it's up to the OS to check our parameters, to make sure that, there's no buffer overflow perhaps, or whatnot. So that, we're doing only legal things. So you have to be very careful when you're an operating system developer to check all of this. If there's even one vulnerability anywhere in here, then the user process could potentially start executing its own code in supervisor mode, in which case all hell breaks loose. Right? So that's the main thing. Okay. So using this nice facility, we have what we might call hardware abstraction layer. Right? So there isn't any way for a process to directly talk to the screen, look at the keyboard, talk to the rest of the world, even read from the disk. It just doesn't exist. The only thing we can do is make a system call and tell the OS, I would please like to read a little bit from this file descriptor. And then we'll see if the OS approves. Right? Usually, if you do the right thing, it will approve. You get a little bit of data back. That ends up probably on your stack, depending. Or maybe you pass in a buffer, in which case the data ends up in the buffer that you gave it. And then you can do some more computing. And then you say, I would like to write something, please. Right? Pass them a pointer. The OS can read that value, do whatever it is that you need to do. Why is it good to have a hardware abstraction layer like this? Why don't we just let the processes talk directly, say, to the printer?
Because who the heck knows what kind of hardware there is? The hardware might think it's talking its own language.
Okay. So that's one reason. So it's nice to sort of have a virtual printer in the sense that you can abstract away all the finer details of the printer. You just say print, and then whatever language it wants, the OS will take care of. But you can do that with a library too. So you can have a library that says print. Why would we have an OS function? Usually you want to keep the OS as small as you can. Because if you have even a slight flaw in the OS, all hell breaks loose, right? So you want to make it really small so that you can make sure there are no flaws anywhere in that code. That's not really how Linux works. But in the academic ideal of an operating system, you make a microkernel, make it as small as you possibly can. So if we could do it in a library, we would always want to do it in a library. There's also, by the way, there's also no performance benefit to running in the kernel. Or there's extremely little performance benefit. Nothing goes faster just because you put it in the kernel. So you might as well run it in the user space. Okay, any other reasons? So, okay, maybe make things simpler through encapsulation. Could use a library. And that's what most people would recommend. And in fact, if you look at printer drivers, I think it would be very unusual to have a printer driver that ends up in kernel these days. Probably it'll be something that you load into your program. Any other idea? Yeah.
What a security thing.
Security thing. Okay.
So if you abstract things out of the user area, then it's not as easy to get the OS to self-serve by some of the things. It's not as easy to exploit being inside the OS, I guess.
So what I'm saying is we should just allow the user to talk directly to the user space program to talk directly to the printer. Nothing else. So you could have, there's an opcode, input and output, I think, or in and out, something like that, depending, in S, out S, something like that. And you specify just what port you want to talk to, and that means something like talk to the serial port where the printer is attached. So what's the security flaw there? Okay, we'll think about that a little more. Did you have an idea?
Yeah, if there's no one to supervise, then we're screwed.
Why? We're well behaved, right? All right.
What do you mean? Like, any program can make the all computer crash?
No, we're just printing to the printer.
Oh,
I'm just adding this facility so we can use the opcode out and in that goes directly to these ports, not to memory. Right? Those opcodes, they don't talk to memory. They talk to those little buses that go to peripherals. And so maybe you haven't done that much of that either. That is probably 362 as well. But yeah.
Maybe if like you have 3 different programs trying to print at once, it's going to cause collisions.
Exactly. So what would happen if you have a collision in the printer?
Data corruption.
You could get data corruption, or you could get like half of the picture, half of your picture, and then half of the other program's picture. It could be all sorts of weird stuff, right? So you have a problem here with concurrent access. You have 2 different programs. They want to use a single resource at the same time. That's going to be a problem, right? So you could imagine, and we haven't talked much about that, but you could imagine dealing with this in user space. So every program on its own first checks with all the other programs to make sure that there isn't a conflict, that no one else is using it, and then you print. So that seems like a decent solution.
Does it actually, that actually lets it be pretty much a lock?
Yes, so, well, no, not in this case, but oftentimes locks are used for managing concurrency. So if we wanted to do this in user space, we could still say, oh, the in and out functions, instructions, they're fine in user space. Now, we just say, oh, programs that want to use the printer, they first have to acquire this lock. We haven't all used locks yet, but we'll do that later in the semester. You first acquire the lock, and then you may use the printer, and then you release the lock so someone else can use it. Okay? Seems fine, right? What's the problem?
What if the program never finishes?
Yeah, that's maybe a good point. You can have a program that just holds on to it forever. It's not nice. But there's also the problem that even if you tell a program that, oh, you have to do this first, if they actually have access to those opcodes, there's no more verification happening here. So they can do whatever they want. It's not like the OS is checking every addition you make to make sure that you're not adding 17 to it, because that's just not allowed. That doesn't happen. No, so if we make the opcodes available, then they will be able to print to the printer whenever they want to. If they're well behaved, then they would first make sure they get the lock so that no one else is using it, but if they're not, they can do whatever they want. So now you can have a program that screws up your printing, even though all the other programs are fine. One program can get in there and screw it up.
Make a queue based on the caller.
Yeah, but how do you enforce this?
If you make a queue based on the calling, so first.
Based on the caller. So I think the problem here is a question of the level of abstraction. So with the in and out opcodes, you can write a byte to the printer. So anytime you want, you write a byte to the printer. If someone else is using it, who cares? I'll write another byte to the printer. Right? It's a problem. So we need someone to keep control here, and in order to keep that control, you cannot allow a user space program to use those two instructions because they can do whatever they want with them. So they're privileged. And the same is true for almost all the instructions except for the regular manipulating memory and manipulating values in registers. In your
There can be one program running at the same time on a single core.
There can only be one program running, period, on a single core. Yeah. So it's either going to be a user space process, or it might be one of the many possible interrupts. There's also some interesting detail there. So say you're running one interrupt and another one comes in. Should you now jump to the next one? So that depends a little bit on the priority level of the interrupts and so on. But we can ignore that for now. Okay, so what the OS does here, it acts as a, I suppose it's called a monitor. OS acts as supervisor monitor for shared hardware. Okay, so it's the only privileged. It's used to communicate with the hardware. So I'm almost willing to bet here that all of the opcodes that you've ever used are the non-privileged instructions. So you've never talked to hardware directly. You've never written to a serial port directly, most likely.
The only thing I've ever done is like system pause. I don't even know if it's an interrupt.
System pause. Yeah, I don't know what that is.
It makes you console.
Ah, yeah, okay.
It didn't like key.
Okay. Yeah, so that's not it. Right. So if you wanted to play with privileged instructions, there's basically two choices. Either you deal with embedded hardware, where there's no operating system, in which case it's going to crash all the time, and since it doesn't have a screen, you won't know what's going on. Right? Embedded hardware is difficult to deal with. Or you do some kernel hacking, which you do in 385, in which case you do have a screen, but since the kernel has crashed, probably you can't print on it anyway. So those are your two choices. What's that?
You're blind either way.
Yeah, more or less. Well, so there's some facilities, but oftentimes it'll just crash. It dumps out something and says, like, oh, these are the registers I had. Like, these are the register values. Okay, forget it. And then you have to try to figure it out. So this is life in supervisor mode. I mean, it feels nice and privileged, but it's actually not all that comfortable. Okay, so 10 minutes. So I thought, let's see. Yes, why don't we do a little bit of an experiment here? We'll try to do a manual system call. So we'll write a little assembly program. You can only make system calls in assembly. Any idea why?
Because it's assembly call.
It's an opcode, like int. How do you make an int in C? There isn't such a thing. Right? So, well, you could imagine making a wrapper function called syscall that you then supply all the parameters to, and that would work. But that's just not how you do things. So there's wrappers for every system call. In libc, there's a wrapper for every system call, and it just does some other nice stuff for you. And we'll try using those as well. So let's just try this out. So what do we call it? .s. So I actually have because there's so much typing in assembly, I have it prepared here. So here's a little program. Let's go with I had a shorter one for starters. Make a really simple one. So we can actually make it even. Oh no, this is good. Okay, so what does this program do? It checks some EDI, one of our registers, to see if it's 1. And if it's not 1, oh, if it's 1, then we go to this no args, and we move 255 to EAX, whatever that means, and we return. Otherwise, we put 1 in EAX and we return. Okay, it's not much of a program, but any ideas what it might mean?
Yes, sir. Upload 255.
No, so there are no system calls here. We haven't gotten there yet. So this is the only way that a program can communicate with the user without using a system call. So what would be some argument that's coming in? This is a regular program, right? I can't try it because then I reveal the secret. So something's coming in EDI. What might that be, right? And then something's coming out of our program, and that's apparently going to be visible to the user. So how does this work? We've done this sort of stuff in C before. We've encountered these things in C. Yeah.
It's not arcs.
Yeah, so this would be argc. Argc goes in EDI, and then the argv pointer is going to be in, I don't know which one comes after actually. SI maybe, might be ESI. Okay, so there's argc, or something very much like it. And this, sticking something in EAX, and then, and what's the result? It's not on the stack. This isn't EAX. It's a register.
If there's no arguments, it's 255.
Yeah, so that's what it's doing, but why? I mean, so the user gets to see this through a little bit of a jumping through some hoops. We can see it at least. What's a way that a program in C, without using printf or anything, can get a value out to the user? Ever used the function exit?
Yes.
So exit 0 usually means everything's fine. Exit 1, probably there's a problem. Any other value also. So you can get that by saying echo $?
What does X255 do?
It doesn't do anything. None of these do anything. They just return that value to whoever run the program. So let's try it.
I believe exit one was supposed to tell the system that something went wrong or something.
No, it doesn't tell the system anything.
Just about it's just for your
You
own
deal
use.
with it.
You just get, yeah, exactly. So if your shell program that we're running here, this is batch that we're running, if it sees that, it might decide to throw up its hands and get very angry, or it could just forget it, and that's usually what it does. But make files don't react that way. They actually get very angry. So if you get a non-zero return value from any of the lines in your make file, it quits. There was an error here, right? So we're not going to continue building this stuff for you. Okay, so we assemble it. Now we have our object file. We want to link it. Why do I call it scall when it's...
It's not that.
Did I not have a start? What's in here? Main. Oh. Let's see if that works. I think I had made this to be compiled with GCC, but I wanted to do it this way. Okay. Great. So, is it supposed to be init? I'm not sure. Okay, we'll just compile it with GCC. I have another one that's ready. Oh yeah, so there's the problem. Yeah, okay. So that actually, yeah, there are certain expectations for an init, I believe. But okay, so you can't quit the program the way you do here unless you're being called from within some nice libc function that prepares stuff for it. You're supposed to exit your program properly, and that actually requires a system call. So this is kind of making our, we're being a little bit complicated here. Like, this is the bottom of my stack. So if I return from here, what does that even mean? There isn't a return address in the stack. I can't do it. So all I could do is commit harakiri, right? By calling the OS and say, kill me, please. Right? So, okay. So that's actually what libc does for us here when I'm compiling this with C. Let's do it. All right, that didn't do anything. But the return code is hiding in here. We got a 0. If I specify a 1, hello. I got a 1. Huh.
Wasn't it subtracting instead of moving one?
Yeah, what did it do? Yeah. Let's tell it one more. Yeah. So the program
Subtracting first.
tells, yeah, so the first argument is the name of the program that you ran. So this little funny program is counting how many arguments there were. Right? But if we didn't specify anything, then then it gives you 0. So actually, I don't know what happened there because
Probably you lost it because you ran nickel bound.
oh no, not that. No. I mean I don't. I thought we had a 255 in there.
If they're equal, go jump to.
Oh, right. That's what I'm saying. Yeah.
Otherwise,
Compare
carry
or
on.
something, you just take that. It's like who's
Look
Yeah,
at
it
this.
should do that subtract, right? It should do that.
What is this nonsense? What is this EDI? It's the wrong. I mean, this code doesn't do anything useful at all. Go like that. That'll be much better. So I think maybe I was playing with it on 64-bit, and there the arguments end up in different registers. Let's try this again. So now I'm hoping we got a. Look at that. Okay, so now it's working. Cool. Okay. But so that was without a system call or without a system call. Let's go for the full what's the word? Full kahuna.
Save that return value?
What's that? But
Where, how, and for how long does the system save that value?
until you there's no system saving anything, but the shell is saving it for you. So the shell is running this, right? And then at some point it stops, and then it gets the value out. I actually don't remember how it gets the value, but it can do whatever it wants with it. And it decides that, oh, if anyone ever types this string out, I will give them the value of that out. But next time you run a program, you get that instead. Okay, so let's just dump this other system call in here. So this is the full thing. Now we're not going to need libc anymore. We have a start function. So what are we doing here? I'm putting a 4 in EAX, and then a 1 in EBX, and then my hello world, ECX, and then 14 in EDX, and then I make an interrupt happen. So what's the 4? Exactly, that's syswrite. Okay, I want you to write something. What's the 1 there? That actually beats me. I can't figure that. Oh, yes, of course. Any ideas? What is the 1? Oh, that's
Oh, it's could you show us what the system call takes?
okay. That's a little bit cheating, but okay. Oh, it doesn't say what it is though, so that's okay. What's an int? Okay.
Writes to standards as opposed to something else.
Right. So we gotta say here. We say what do you want to write? How long is it? But where do you want to write it to? Right. So that's a file descriptor. What's that?
What's 2 standard error? Is that-
Yes. 2 is standard error. 0 is standard in. Yeah. So
What if you write the standard in?
if you try to write to standard in, you're probably gonna get an error message back. So it just won't do much for you. So that error, it'll end up in EAX as a return value from that function call, and it'll be a -1 or something. Okay, so here we're doing that system call, and then finally, at the end, we're saying, what? System call 1, with a 0 for error code, and then we make the interrupt. System call 1, sys exit. So return exit with error code 0. So let's just compile this, and then I'll let you go. Oh no. Whee! There it is. Okay, so I'll see you on Monday.